Well, welcome everybody. Please welcome Sebastian Opper from University, who is going to talk about derived Picard groups and integration of Hochschild cohomology. Thank you, Sebastian, for coming.
Thanks. Yeah, no, thank you for inviting me to the seminar. Kind of the title says it a little bit. So we talk about derived Picard groups. I will tell a little bit what they are, and give sort of different characterizations of them. And then the connection to Hochschild cohomology, and the idea is that sort of you can pass between the two, a bit similar to the relationship between Lie groups and Lie algebras. I try to motivate everything. Because I didn't quite know, given this is an online seminar, who will be attending, I try to hopefully take everyone along by giving enough definitions, but hopefully not too many. We see. First part is to maybe start what are derived Picard groups, so explaining the first part of the title. So if you give them a DG algebra, and even though you can perfectly just take an ordinary algebra, I at least invite you to think of a graded algebra, because most of the things I will be talking about kind of collapse and get very boring if you just take an ordinary algebra. You'll see later why. But you can also take something more general than this. So in a given setting, if a DG bimodule, which is to say an object in the derived category of this enveloping algebra, this is called invertible if there exists another such DG bimodule, so that if I tensor x and y from one side by the derived tensor product, this is isomorphic to A, which I consider as a bimodule itself in a natural way. But if I tensor the other way, I get the same result. And the derived Picard group is not a group which consists of all these invertible DG bimodules, modular isomorphism, and then it has a multiplication given, as you might have guessed, by the tensor product, the derived tensor product over A, and then the neutral element as well, the diagonal bimodule A. Okay, so that's a group.
Sorry, just a question. So are you thinking of bimodules or objects in the derived categories, or this just concentrated in one place, or the...
Okay, I think when I say DG bimodule, like if say A would be an ordinary algebra, this would include like chain complexes of bimodules. It's just sort of the DG part, sort of, and codes this. So if you would sort of fold them all up and take the direct sum, so that's sort of the idea. So this incorporates, for example, chain complexes of bimodules in the ordinary sense. And so there's different ways to get these derived Picard groups. So for example, like one way to view them is a sort of generalization of automorphisms. So if F is a algebra automorphism of A, or DG algebra automorphism of A, then the usual way to assign a bimodule to a functor, you just do this. And then this gives you an element in the derived Picard group, and then revertibility essentially comes to the fact that this is an algebra automorphism. If I give you any element in the derived Picard group, I can go and just tensor with it. There should be an A here. I forgot this. And this gives you a functor between the derived categories from A to the derived category of A to the derived category of A, and this is, by the way it's defined, triangulated, and it's co-continuous, meaning in this case just as coproduct preserving. So this is an autoequivalence. And then this assignment induces a homomorphism, and I just say what this is. So the first step is to say, well, okay, from X we assign this X lower star, which gives us, as I said, a co-continuous triangulated equivalence of the derived category. Now those things I can always restrict to the compact objects, and the compact objects are exactly the perfect complexes. I would say something about this in a second again. And you still have a triangulated functor. So overall, this is compatible with compositions, and you get with multiplication, and so you get a group homomorphism from the derived Picard group into the group of triangulated autoequivalences of this triangulated category. So in some cases, this is known to be injective or surjective. And although I don't have a concrete example where it's not one of them, there's a related problem, which is slightly more general, where it's known to fail. So you can do the same kind of thing by just taking an arbitrary DG bimodule now over possibly different DG algebras, let's say. And you can, in the same way as before, while the tensor product derived from this a functor between the derived categories. And this is known to fail to like this correspondence from bimodules to these kind of functors is known to fail to be injective or surjective in general. And this is related, in especially algebraic geometry, where this kind of questions were studied to the existence and uniqueness of so-called Fourier-Mukai kernels. For those people who know this, I don't know if I will get to this today, even though what's promised in the abstract, I noticed I have a slightly different shift. This will appear again, or maybe not, we'll see, depending, time permitting. But so this comparison map between equivalences of this triangulated category and the derived Picard group, even though it's not perfect, it exists, and maybe sometimes it's objective or subjective. You can say, okay, like still you can regard this as a sort of symmetry group of the perfect complexes and the derived category. But because we start from DG bimodules, it inherently takes into account the structure that we have, which is DG category. It's not just a triangulated category, it has a DG enhancement. And so you can think of this as an enhanced version of a symmetry group of either of these two categories. So what we're studying when we study derived Picard groups are symmetry groups of triangulated categories plus something in an enhanced way. Okay. Now, there's an alternative definition, which is maybe a bit more, yes, more technical at first, but it's the one we sort of need and is more practical for our purposes. I try to break it down as good as possible. So there's an alternative equivalent definition of the derived Picard group. And this uses A infinity functors. And I will say in a second, roughly again, what this means, in case you're not familiar. So sort of similar to triangulated functors between perfect complexes, you take now so A infinity functors between perfect complexes, and they also come with a natural enhancement. And then F needs to be invertible up to some equivalence relation, which I will denote by this approximate sign. And then you take the same way you took sort of isomorphism classes of bimodules for the derived Picard group. In this case, you take equivalence classes of functors. And there's a sort of more concise way to write this down if you use some model categories. So the category of all small DG categories, they form a model category, and then you can take a homotopy category. And then if you take the automorphism group, the actual genuine automorphism group in the homotopy category of the perfect complexes, which live because it's a DG category inside of this, then the derived Picard group is just this automorphism group. This is nice for conceptual things. This is the best one for us, and the easier definition, although also not as general as this one. Sorry, was the first one. So we mostly kind of think of this alternative definition via A infinity functors. Okay, and just because I didn't mention this before, depending on your familiarity with DG algebras or not. So if A is an ordinary algebra, there's no differential, no grading. Then the perfect complexes is just a familiar homotopy, bounded homotopy category of projectives. But again, sort of this is the kind of case where everything is a bit boring. So, but maybe this gives you obviously some intuition. And so what are infinity functors? I'm not going to define them strictly because that would take too much time. But if I give you two DG algebras and an infinity functor between them is then a collection of maps, which are linear maps. And it takes several entries in A and then spit out one output in B. And sort of the arity of the operations and the degrees with some of them is equals to 1. This was something that will show up later. So did someone? Okay. And then they're supposed to be sort of interlocked with each other to satisfy certain compatibility or coherence conditions. And one way to read them is that F is sort of not necessarily strictly covariant, in case this was like a functor between, let's say, categories, So it respects composition, but as sort of correction terms, and they come from these higher operations here, and that kind of corrects the failure to be strictly covariant, and then, well, you have sort of corrections for those, and they build up a kind of family of coherent systems of homotopies, if you want. So you can say, okay, then A infinity functor is a covariant functor up to homotopy. And then, so as a special case, if I give you a DG algebra homomorphism from A to B, that's the same as to say an A infinity functor from A to B, where this first part, and the G1 part just means like where I equals 1. And, well, GI in general means where we have arity, this is the arity I, operation of arity I, where this is 0 for all I greater than 1. So you can view these things, DG functors, to be also homomorphisms, as special cases of A infinity functors, but sort of a very, yeah, much less rigid generalization of them. And then just to mention this, because like here, these are categories, so we need the notion of A infinity functors between categories. It's basically the same thing where you just compose a number of composable morphisms to one instead of I elements of A. But it has some extra map, which sort of is superfluous in this case. So of course, like every functor, you want to see what happens to objects. So in the case of algebras, of course, this is not any real information because these are sort of categories with one object. So it's not much you can do. So this is why I left it out, but in general, you have to sort of add 0, what is usually multiplied. So yeah, maybe the takeaway from the slide is, okay, derived Picard group, something A infinity functors on perfect complexes up to some equivalence relation. This is maybe enough to remember. And then functors, A infinity functors, these are just collections of certain multilinear functions. Okay. Right. So then the derived Picard group in general is kind of difficult to compute. And the reason is that I said, well, it's sort of the, morally at least, the symmetry group of some very big triangulated category. Even the perfect complexes are kind of large. So you would expect, given that this has to respect all the structures, see all the interior structure of the category, that is, well, they're not so easy to get your hands on. Nevertheless, in some cases, they're completely understood. And this is usually sort of case by case, ad hoc studies, and they'll use sort of different tricks and different observations in the case at hand. So there, the list I give you is obviously not complete, but it sort of, these are examples which share a certain similarity between them, which you would see in a second. So I guess one of the earliest examples where they were computed are commutative algebras, which goes back to Yekotieli. So if A is a connected commutative algebra, meaning it's just not a product of several other ones, then the derived Picard group is isomorphic, sort of has two pieces. So it's a semi-direct product, and then one is the automorphism group of the spectrum of A, which you can also rewrite in other terms, but I wanted to sort of have the geometric point of view on this. And then a sort of more algebraic bit, where the Z part, the integers, this is just a shift functor, because although it's maybe not apparent from the definition, the shift functor is always an element in the derived Picard group. And then this is the ordinary Picard group of this affine scheme. And you have something similar. So if you have a nice and smooth projective variety, then a very well-known theorem by Bondar and Orloff says that you essentially have the same decomposition. The derived Picard group is something geometric, the automorphism group of X, the shift, and then something which I personally would put more slightly on the algebraic side. Maybe it depends on how you look at it. That's the Picard group of X. And then there's a class of derived discrete algebras, which also fall into the class of so-called gentle algebras. These will appear later. And it was proved by Bohm, Hadcock, Steller, and Bloch that the derived Picard group, although they didn't write it like this is sort of like a maybe more modern viewpoint on a theorem, is that this is also a sort of two contributions. One is the shift, and then some sort of multiplicative group, K star, and then the mapping class group of a surface, sigma, which is a cylinder in this case. Don't need to know what this is, it will appear later. But this is some symmetry group of a surface in this case, a topological manifold. And this is some algebraic something. And you can also like do this, for example, for Brauer-Star algebras, which goes back to Smaller, Volkoff and Smaller. And what they all have in common, this is why I selected them, is that the derived Picard group kind of splits into two pieces, into a semi-direct product, and sometimes it's actually a product, not just a semi-direct product. And G is sort of more geometric in a sense, the symmetry group of some object like a scheme or manifold. So these examples here. And this is also true in the fourth case, Brauer-Star algebras. So the G there will be like a braid group, which you can view as a automorphism group of a punctured surface, for example. And then N has a slightly more algebraic flavor, also in this fourth case. Yeah, this is just a maybe interesting coincidence in a sense, but this is also like a sort of widespread scheme, if you want. We'll see this later. Okay. Right. This is algebraic. Okay, so the second keyword in the title is Hochschild cohomology, which I also want to say something about. And now just like a little bit, and then in some more detail later on. And I guess many people know this, but just to be on the same page, I wanted to be sure and include this. So again, so A is a DG algebra, and we can define its Hochschild cohomology. And that's, you can take this as a definition, the graded endomorphism ring of A inside this derived category of bimodules, DG bimodules. So that would be this, but then also well-known alternative way to compute this is to say this is the cohomology of one specific complex, CA, which is called the Hochschild complex. And the definition, we will see this again, I guess, at least 2 times. So if you haven't seen this is a bit too much at once, it's fine. This is so like the nth homogeneous component is just it consists of a product of multilinear functions. So something we've kind of seen for A infinity functors as well. This also consists of tuples of functions with like higher and higher arity. And as before, like the arity and the degree are kind of linked. So like the arity plus the degree equals the degree in a Hochschild complex in this definition. And then it's graded algebra. This is a graded algebra because, well, this is an endomorphism ring. We have composition. This also admits a Lie bracket, which is compatible with this. And this is called the Gerstenhaber bracket. And this turns not the Hochschild cohomology strictly, but the shift of this into a graded Lie algebra. So for example, if you take the first Hochschild cohomology and take the bracket, sorry, if you take the bracket of 2 elements in the first Hochschild cohomology, you don't get something in degree 2, but again, something in degree 1. So sort of with respect to this grading, this will be degree 0, and this is why, so yeah, why you have to shift. We see sort of like everything a bit more explicitly a bit later on, but for now, this is just the overview. This is the general structure. And then in this kind of framework of the Hochschild complex, if you have an A infinity functor, you had these components, Fi, which were just some multilinear functions. And because the n here was basically 1, not that you maybe recall the definition, but I just tell you the n here was always 1, this defines an element in the Hochschild complex. If I take all of these combined as one element in the Hochschild complex. I can also do something similar with sort of the structure maps from my DG algebra. So DG algebra consists of its differential and its multiplication map. And now the differential is of degree 1, the multiplication map is of degree 0. So if I write mu as the element which consists of the differential in the kind of arity 1 part, and then of m in the arity 2 part, and then 0 otherwise, this defines an element in C2 of the Hochschild complex. So both functors, A infinity functors, as well as sort of the structure maps of my A infinity, my DG algebra live naturally in this Hochschild complex. Okay. Before I go back sort of in more detail to Hochschild cohomology, I want to say, okay, well, so what's the connection between the known connection between derived Picard groups and the Hochschild cohomology? So this goes back to a theorem of Keller, who proved that if A is an algebra, although this also works more generally, then there's a sensible way, let's say, to assign a graded Lie algebra to the derived Picard group. And this is a bit similar to how to assign a Lie algebra to an algebraic group, very similar formalism. And then there's something you actually have to prove, doesn't follow from the definition at all, is that that this Lie algebra that you define in this way recovers the Hochschild cohomology. And what this in particular means is, which I didn't say before, but the derived Picard group is a derived invariant of A, more or less by definition. And through this connection, this means in particular that also not only the Hochschild cohomology, but also its Lie algebra are sort of derived invariants of A. So this whole Lie algebra in itself is invariant under derived equivalences. And so we have this relationship between a group and a Lie algebra. As practice shows, I guess, maybe someone would argue with this, but I would say this Hochschild cohomology is like, this is well known in much more examples than the derived Picard groups, and it's easier to compute. And you might argue why. Well, I would say that the Hochschild cohomology is sort of local nature, and one of the reasons is that the Hochschild complex, well, it's just a complex defined, it just uses A, no perfect complexes, no derived category, nothing. So you can just compute it from A directly, whereas if you, well, consider the symmetry group of, well, the derived category or perfect complexes, this has to see the entire structure, and so this is a more global object. So you have this discrepancy between sort of on one hand, like a global thing, which is usually easier to compute, and another thing which is of more global nature, which is usually harder to compute. And the idea is still that, okay, you have these things which are in a relationship together. Can we extract parts of the derived Picard group, at least from its Lie algebra, which we now know, which is the Hochschild cohomology? And to motivate this, I want to compare this with the situation where this can be done. And this is Lie groups and Lie algebras, where sort of this relationship between global and local information works really well. So in a very abstract, vague terms, the relationship is as follows. So from a Lie group, you can go to its Lie algebra, which is defined as a tangent space, a neutral element. But you can also go back. And this depends on how you want to phrase this, but one way to do this is sort of via a so-called exponential method. And this process, in this generality in which I wrote this down, loses information. So if L is the Lie algebra of G and G lower circle is the identity component of G, then the exponential, for example, will always land in the identity component. And the reason is that it's based on the way it's defined. So the Lie algebra is the tangent space at the identity, at a neutral element. So it only sees the local neighborhood of this. But then the way it's defined is you, well, regard these elements in the tangent space, you identify them with vector fields, and then you follow the flow of your given vector field by starting from the neutral element and then following this flow until a certain time. But if you start in the component of the neutral element, or what I call identity component, then of course you have to stay in this identity component, and therefore you can't leave it. So this is one obvious sort of drawback. You will lose the other identity components immediately. But it's not so bad in a sense, because it has some very nice properties. So if you're very close to zero in a small neighborhood, which I usually know by you can ask this question of, okay, if I have an exponential and another exponential of something, and I take the product with respect to the group law, can I write this as an exponential of something? And the answer is yes, you can. There's a sort of distinguished element, as long as you're close enough to zero. And this product here, and it's called the Baker-Campbell-Hausdorff product. And this first starts as an addition of U and V, but then this is deformed by terms, and this is like an infinite, this is a series, by terms which have some fractions, and then this continues by having more and more nested, iterated brackets of U and V. So, and obviously for this infinite sum to make sense, you need some convergence. This is one of the reasons why you need to restrict to a small neighborhood around zero. But let's assume this just makes sense. Then what this formula plus says essentially is, well, the exponential, when restricted to this small enough neighborhood and equipped, which is equipped with the Baker-Campbell-Hausdorff product, and defines a group homomorphism. This is exactly what this plus means. And implicitly what this says also is, yeah, this actually defines a group law, this Baker-Campbell-Hausdorff product, and it does. But so the upshot of this whole slide is, if you want, is so from the Lie algebra, let's say I'm only given the Lie algebra and I know nothing about the Lie group. At least in a small neighborhood around zero, I can recover not only parts of the Lie group, but I can also recover parts of its group law, because of this Baker-Campbell-Hausdorff product and this compatibility. So, for example, assume the exponential is injective when you get a subgroup, right? So you can see part of the group structure just through the Lie algebra structure. And what we want to do is to sort of copy this formalism in a completely different setting of derived Picard groups and Hochschild cohomology. There's maybe some classic example. So if G is the general linear group in 1R, so this is just the non-zero real numbers, then the Lie algebra is R, or more appropriately, the matrix, 1x1 matrices over R, and with the commutator bracket, this vanishes because it's commutative. So the bracket is 0, and the exponential is the usual Euler exponential. So there's the sum, factorials, and then a product. And in this case, the Euler exponential is injective. And the image is exactly the identity component. This is not connected. This is two components, and this is the identity component. In general, the exponential that does not need to meet everything in the identity component. It doesn't need to be subjective on the identity component. It's sort of lucky accident here. And the Baker-Campbell-Hausdorff product here is very boring because the Lie bracket vanishes. So all the other terms I used to have, other than u plus v, disappear. And then you can recover basically this formula, which you know since analysis 1, that the Euler exponential of u plus v equals the product of the two exponentials. Okay, but in general, the point is it's not injective, because in general, the kernel of the exponential is isomorphic to the fundamental group of your Lie group. And so, for example, if you replace R by the complex numbers, and then for any n, this is Z, and then this is non-zero. So in general, it's neither surjective on the identity component, it's also not injective. So it has a lot of downsides, the exponential in a sense, but it's, still gives you a lot of information. So the summary is, okay, with the Lie algebra of a Lie group, we can recover a subgroup of the identity component, and you can also recover the group law reasonably locally because it's encoded in the Baker-Campbell-Hausdorff product. And as I sort of hinted at in the previous slide, the idea is now you want to find a similar relationship between the derived Picard group and the Hochschild cohomology. The obstacle is somehow that, okay, we're completely different settings, there are no vector fields, there's no notion of integration, and then at this point, there's also no topology or anything. So conversions and all this stuff doesn't make sense. But the idea is that sort of, if you stick with this formula for the Euler exponential, e to the power t, you try to understand this in a very different context and what multiplication means. It's a sort of the trick. We will see this later, how you can make sense of this. Okay. So now what we need for this, in order to do this, is some more structure on the Hochschild complex, not only its cohomology. And at this point, we start with just a graded vector space. We don't need an algebra structure on this or something. At this point, just a graded vector space. And then we can do the same definition as we did before for the Hochschild complex, because all we needed for this is the graded vector space. And okay, we don't have a differential or anything at this point, it's just a graded vector space, but the same definition makes sense. And this structure admits a product which is non-associative, called the composition product, usually denoted by star in this case. And it's roughly defined as follows. So if I give you a function with R inputs and a function with S inputs, then the composition product will have R plus S minus 1 inputs. And how is it defined? Well, if I give you two functions, what can I do? I can plug the output of G as one of the inputs of F. And this is what I do, and sort of to not discriminate. One of the entries I just sum over all the possibilities, and then I take an appropriate sign, which I'm not going to go into. But this is sort of all what the definition encompasses. The signs, though, are important. Yeah, you can explain them. So what is the connection to like the G algebras or infinity algebras, which I haven't talked about, but we sort of can with this formalism? So if I give you a map, which could be differential, but at this point you don't know if the square of it is 0. And you have a sort of candidate multiplication map, which you also don't know if it's associative or compatible with differential. Then you have a very handy way of phrasing whether it is triple here as a DG algebra by saying, well, a certain element mu has, if multiplied with itself in this composition product, is 0. And what is this mu? This is exactly the thing we saw before. This is the one where u1 is d, u2 is m, and mj for all the other ones is 0. So this is the structure element we had before. Talked about this. So you can very conveniently phrase this compatibility of associativity, compatibility of m with the differential, and the fact that d is actually differential just in one equation. And you can go one step further and say, well, if I just have an arbitrary element mu in C2, and I assume that its 0th part is 0, and it satisfies the same condition as before, then if you flesh this out, what this means, this is what people usually mean by an A-infinity algebra. And you can take, if you want, as the definition. And this just means like all these mu i's, they're operations, they're part of this A-infinity structure. So this is sort of already see also a very handy operation to have because it lets you phrase things very effectively. Okay. And then this product here is not associative, this composition product, but if you again shift the complex a little bit, this is not associative, but still belongs to a class of so-called pre-Lie algebras. And why they're not associative, but they're still good enough so that if you take the graded commutator, you get a graded Lie bracket. So if you take this definition here, then this is a graded Lie bracket. And if A is a DG algebra, and you have the structure element mu that we had before, encoding the differential under multiplication, then, well, this doesn't depend actually on this, but this is just the graded commutator of the composition product is just the Gerstenhaber bracket. You can take this as a definition. And then the differential, I can also define out very easily. Well, in this case, I need a structure element. I just take the bracket with it. And then because this is of degree 2, so that means it's of degree 1 in the shifted Cauchy complex, this will be of degree 1. Okay. You can go one step further and say, okay, instead of just taking one function that I plug as the input of another function, I can generalize this to the so-called brace operations, of which the composition product is just the lowest order case. So this takes one function f and then a bunch of functions g1 to gn, and I can do the same thing as before. I take a signed sum over all the possibilities of plugging the outputs of g1 to gn as the inputs of f. And if I, for example, have more outputs than inputs, this is just 0. And otherwise, the only thing you have to make sure is you're not changing the order of the GIs. So you just keep that, but you're allowed to sort of choose at which way you put them as inputs. So the definition is very similar. And what this allows you to also recover the algebra structure on the Hochschild complex and the Hochschild cohomology. So if A is a DG or an A-infinity algebra, then the same is true for the Hochschild complex. And the way you do this roughly is, okay, instead of just taking the bracket with mu, you take now these brace operations with mu, and this gives you, in case where A is the DG algebra, this stops at n equals 2, and you're done. And this gives you what is called the cup product. And in other cases, you have higher operations, so you can still do the same. And in particular, if you go to cohomology, then this recovers the multiplication we had on Hochschild cohomology, which it had by definitions as this endomorphism. So this all comes from these brace operations and the composition product, all the structure. And then all this together, they can be combined into something which you don't need to know. I'll just throw it out as a term because I will appear one time later, is that they're combined into something more complicated. It's called the B-infinity algebra structure. And then Keller showed that this structure is also derived invariant. And from this the invariance of the Lie bracket, the invariance of the product, the invariance of everything follows, basically. So this is sort of the strongest form of all this structure. Now what we want to do is we want to use all this extra structure we have, which we can't see on cohomology, the brace operations, the composition product, to define this exponential map. All right, but before I decided to give a summary. So I think it's useful. So if we started with the great vector space and then say, okay, we have the Hochschild complex defined in the usual way. This has a non-associative product, a composition product, and some extra operations, which are called brace operations. They're all defined in the same way by just inserting functions into other functions. And then the graded commutator defines this Lie bracket, the Gerstenhaber bracket. And then if you have an extra structure on a vector space, a DG or an infinity algebra, then you get a structure element we talked about, and that this has this property that the composition product with itself is 0. And then you can use all of this to put the same type of structure on the Hochschild complex, which then is compatible with everything because it all comes from the braces. So it's compatible with the Lie bracket, and then the shifted Hochschild complex is a DG algebra. So everything we've seen already before, just on one slide. And then what we see in the last bit is this, all the structures that the Hochschild complex has. For example, the B infinity algebra structure are then derived invariant. So this is all a very, very sort of rich, structurally rich object, which is also very, very, sort of has an intrinsic, in terms of derived equivalence, intrinsic meaning. Okay, so as I said, what we want to do now is we want to define this exponential from some neighborhood in the first Hochschild cohomology, whatever this means at this point. And one obvious question is why only the first Hochschild cohomology when the whole Hochschild cohomology was the graded Lie algebra? It's sort of where it's like you wouldn't expect anymore. And one of the reasons is, is that, well, A infinity functors, which are objects in the derived Picard group, what we had as well, the associated element lives in C1. So this is one of the reasons why you would only expect something in the first Hochschild cohomology, but there's also limited interpretation of what these other Hochschild cohomologies would mean in terms of homotopy groups of some objects. Okay, so this is what we want to do now. So how does this integration stuff work? If I give you a DG algebra or an infinity algebra, then I can filter my Hochschild complex very simply by subspaces, and they're defined in exactly the same way. The only difference is that I don't start at 0 with I equals 0, but I start with n. So things in this part here are just tuples of functions which have at least m elements. And then, of course, I get the descending filtration, which is Hausdorff. And this is called the weight filtration or tensor length filtration for Western people. And then all of these are DG subalgebras. Basically, because if you plug a function with m elements into another function with m elements, you get at least, not elements, arguments, you get at least a function with at least m arguments. So they're closed under all these brace operations, in particular a composition product, which implies directly this. And then, so if you view them as neighborhoods of 0, that gets smaller and smaller, these WICs, well, with this topology that is induced, this turns this Hochschild complex into a non-vector space, which is complete with respect to this topology. So a function is like an element in a Hochschild complex is very small when every of its components has a lot of arguments. And then in this kind of world, you can now define the Baker-Campbell-Hausdorff product as long as U and V are in the second filtration step. So they have at least 2 arguments, C+. And you use the topology to say what conversion means. And well, you have the Lie bracket given, so you can perfectly define now this product. And then it's just a general theory argument that this is a group. So the C1 plus, if I restrict to degree 1 elements, then becomes a group. Associative and invertibility, everything is kind of, this is a general argument. And now this filtration that I have from 0 C plus to C, this induces a filtration on cohomology, and the middle part I call HH1 plus by analogy. And then sort of everything I have on the cochain level then descends to the cohomology, because I can still define this whole bracket on the Hausdorff product because I have a Lie bracket on the cohomology, and this becomes equally group.
Okay. Can I ask something?
Sure.
I don't understand where the norm comes.
Yes, so you say it's like a norm where you have just so you say two objects, like I don't know, the norm of a something is the inverse of 2 to the power, and then the smallest index in which it lies in this kind of subspaces. So for example, something which lies in W2, so in C plus, but not in W1, would have norm 1 over 2 to the power 2, so 1 over 4. And if you're in 3, you're in 1 over, the norm is 1 over 2 to the power 3, so 8, and 1 over 8. And so like it gets smaller and smaller. That would be the norm, how you define it.
Thank you.
Does this answer? Okay. So, and then, yeah, this is complete. And then you have sort of topology and everything, so you can make sense of all these equations. Okay. So now we get to the exponential, sort of a precursor of this. So if you have characteristic 0, you can just copy the formula from the Euler exponential and say, well, you'd write it the same way, but now instead of multiplication, you have this composition product. But this is not associative, so I need to say what it means to take the ith power of this, because it depends on the bracketing. And so what you do is you define it inductively like as so. And then after the power 0 is the identity, which is just an element of from A to A, right? Which lives in a Hochschild complex. And then, this is maybe confusing notation. So what this means here, maybe there's a bracket missing. So the exponential of f is an element in the Hochschild complex, and this has different components depending on the arity of the entries. And the arity 1 entry is exactly this identity here. So the reason this converges is essentially if you take something which has at least 2 arguments, the function, and you take its powers, then the resulting function will have at least a plus 1 arguments. And so in the kind of topology, this gets smaller and smaller. And this is why essentially this sum converges in the topology of the Hochschild complex. Yeah, right. Okay. And then the theorem we can prove is, okay, suppose that the characteristic of your field is 0 and A is a DG algebra, or you can go very general, which is called the C unital A infinity ket U, and this encompasses everything I ever encountered in algebra. And it's also useful in some cases like Fukaya categories. I maybe won't say much more about this, but it's useful to have this generality. You get an exponential map, and this is as you may expect at this point. So this is a map from the Hochschild cohomology, this kind of subspace equipped with the Baker-Campbell-Hausdorff product into the derived Picard group. And something I want to mention is that for Lie algebras and Lie groups, you sort of have this finite dimensionality built in. So these Lie algebras are always finite dimensional. And so it's not clear what happens in the infinite dimensional cases. And in this case, you don't need any of this. So the Hochschild cohomology and even the subspace can be perfectly infinite dimensional, and there will be examples of this later on. And still you can integrate. So there's no obstacle about this. And then something I didn't mention, so the exponential of Lie groups and Lie algebras is factorial. So this is natural in maps between Lie algebras and use maps. So you get a sort of commutative square. You don't expect something like this because Hochschild cohomology is not functorial, but it's functorial sort of under quasi-equivalences at least. So the best you can get is sort of a commutative real one like so. And it basically says, well, if I have a DG algebra and I have something which is, for example, quasi-isomorphic, then it doesn't really matter in terms of the exponential with which one I work with, because this commutes. And you also have to show that these kind of maps exist and so on. That's a different story. But it gives you the freedom, because often sometimes maybe you have one category defined by general nonsense, but you have a much smaller model for this, and then you can use the smaller model if you want to compute the exponential if you want. But then on the other hand, if you have a category and you kind of don't want to replace it by something better, which also has its merits, then you can usually do this because this, yeah, as I said, I never encountered anything which doesn't fall really in the category. Okay, so as proof is roughly as follows. So yeah, I hope it's not too much. But so the first step is to say, well, if I have the exponential, do I get A infinity functors? And then this is where they use the theory of pre-Lie algebras. This is why I mentioned it, in particular work of Gerstenhaber Lie. You can use this to show that, well, if you take a Hochschild cocycle, then the exponential will just by definition sort of an element in the Hochschild complex per se. But then we had this relationship between A infinity functors and certain elements in the Hochschild complex. And this is exactly where you can sort of use this. So you can show that this is an A infinity functor. And then by general theory, this extends to an A infinity functor between the perfect complexes, which will then be invertible in a certain sense, and therefore an element in the Derived Picard group. That's sort of step one. And then the second step is that, of course, this descends to cohomology. So it doesn't depend on I can add a co-boundary. But this is much more difficult, as it turns out, because sort of we had this equivalence relation of functors, and then we have this equivalence relation of cocycles, and they're really, really not compatible in any fathomable way a priori. And so that makes it much more difficult. And the trick is to phrase this in a completely different way. So I said, like, this thing exponential of A of H as sort of the first Taylor coefficient, the one which has just like the arity one operation, is just the identity. So if I just discard this, I get an element in here. And then this happens to be, because this is an A infinity functor, a so-called Maurer-Cattan element of the A infinity algebra structure on the Hochschild complex, not the Lie algebra, which is often what people look at. So this is kind of in the realm of deformation theory. And then you replace this relation that we had in the alternative definition of the Derived Picard group, the equivalence relation of functors, by some sort of stronger relation. And none of these are extraordinary. Like for people who know about this stuff, they certainly know these two relations. And then the trick is to say, well, there's also different notions of equivalence from our Cattan elements, and they all look very different, but they're all equivalent, which is also highly non-trivial in many cases. And then for like good enough algebras or categories, this stronger equivalence relation agrees with one of them, and then a completely different one interacts well with the exponential and the differential. And so you can use this to then sort of establish all of this for sort of good DG categories, and then have the A infinity algebra category, whatever has a good replacement. And then you kind of use the invariance of this B infinity algebra structure, so a much stronger thing than just the invariance of the Hochschild cohomology, which is a theorem by Keller, to establish both the existence and the naturality that I talked about at the same time, basically. But you need to sort of go this intervening step. So like this is surprisingly difficult, which I don't know, often it's kind of, this is the easy part to check that something descends to cohomology, and then maybe defining the function at first is a difficult bit, and here's kind of sort of reversed. Yeah, there's another part which sort of intrinsically is in there, that the wave fluctuation is preserved, which defines this HH1 plus, but let's just forget about this. So, and just one thing I want to say, so I don't know an example where the exponential is not injective, but there's an indication, and also by analogy you wouldn't expect this, that it's not, and sort of the kernel, if it exists, has to do with this comparison between these two equivalence relations, essentially. So there's a very sort of analogy to the Lie group thing. You can view this kernel as something specific. Okay. So and then, yeah, just one thing. So there's a general criterion you can prove about injectivity of this exponential. I will just give 3 families, which I think is kind of covers a lot of cases where this is the case. So the exponential is injective in any of the following cases. So if A is formal, that means it's just quasi-isomorphic to its cohomology, and an example would be if A is just a graded algebra or category. So there's no differential or anything. Another example is when A is cohomologically Schurian, that means in degree 0, it's just K. And there's an analogous thing for categories where each of the objects has just endomorphism ring in degree 0, which is isomorphic to K, but then in the rest of the degrees you don't care. So for example, if you take the collection of simples associated to the algebra, they have this property. So this would be like a standard sort of example of these kind of categories. And then if A is an E2 algebra, we completely forget what this means. Examples are commutative DG algebras. So it's a kind of big class, and then something which is not strictly commutative, but sort of a bit close, are cochain algebras over any topological space. Now, I don't think I will get to this. This is originally was part of the talk, but yeah, you see. And then some exotic example are Hochschild complexes, which yeah, you can do, but it's not maybe the more interesting part. But now what I want to talk about is how does the image of the exponential relate to, well, this was the whole idea, right? The exponential recovers part of the identity component of the derived Picard group. At least that's the slogan sort of we want to follow. It's hard to say in general what identity component even means. Need a very flexible definition. But okay, we can sort of heuristically start to think about this and see where we get. So we compare this like in the easiest case when A is just a finite dimensional algebra with no grading, no differential. And the theorem of Fukaya says that the identity component, which you in this case can be strictly define in the sense of schemes, that this is the identity component of the auto-automorphism group. So kind of a very familiar, which just depends on A, there's no derived. So, theorem by Hochschild, Zimmermann, Saurin, and then independently by Roquier, which says that if A is a finite dimensional algebra, then this identity component of the auto-automorphism group is a derived invariant of A. And just to be sure, I say this time, that means if B is another algebra, no grading, no differential, such that the derived categories agree, then the identity components also agree. And although this is not proved this way, you can view these two results sort of conceptually, like in a sort of logical dependency. So what I mentioned earlier is the derived Picard group is a derived invariant. So if you believe that in some sense the topology is 2, you wouldn't be too surprised to say, well, then its identity component is 2, a derived invariant. And again, although it's not proved this way, if you pretend this topology part is a derived invariant is true, then you would expect the second theorem by Hochschild, Zimmermann, Saurin, Roquier to follow from the theorem of Fukaya, from a conceptual point of view, at least. And then if you make this slightly more general and say, okay, A could maybe be an ordinary algebra, but B is just a graded algebra. I allow graded algebras now. This is already false. So an example is very easily given. So A can be the chronic algebra, and B, this kind of, well, half algebra modular sum relations. This is a so-called graded gentle algebra, for those who will come later. But the derived equivalent, but these auto-automorphism bits, which you can also still define in the graded bits, look nothing like each other. So for example, if A and B are these two algebras from the previous example, then the part you can integrate the H1 plus. Remember, the exponential is injective, so this is just the image of the exponential. This is exactly the auto-automorphism group of A, but on the other hand, the auto-automorphism group of B is 0 in this case, which is not hard to see. And the auto-automorphism group of A in this case is the projective linear group over your field. This is connected to the automorphism group of the projective line by the usual derived equivalence. And so the problem is that sort of, yeah, like somewhat individually, these groups change, but the hope is that you can assemble them into something which is sort of invariant. So if you have any graded algebra, then the image of the exponential, which again is just h1 plus of, well, in this case, a and a instead of b and b, they assemble into a subgroup of the derived Picard group, and this is always the semi-direct product in this case. And just as a sanity check, so the idea is that this is sort of a candidate map for the identity component when A is a graded algebra, to remedy the failure of the auto-automorphism group to be invariant under derived equivalence. But so if A is graded is concentrated in degree 0, so an ordinary algebra, then one can show easily that this HH plus part vanishes. And this is why I was saying if you just consider algebras, everything I say in here is kind of boring, because the exponential contributes nothing. But then on the other hand, okay, this just reduces to the auto-automorphism group, which we know is a derived invariant. And the expectation is that the composition of this out circle infinity into what is the exponential part and what is the auto-automorphism part, this can change depending on if you go to derived equivalent graded algebra. But the idea is that the whole group together, the semi-direct product, does not change. And then if you believe that this is actually the identity component in some way you can define, then you would believe that this is the derived invariant. So that's the conjecture. And there's some extra assumptions you have to make, which are clearly necessary and can be taken care of somehow, but this requires extra work. But the conjecture is now, well, this is derived invariant at least. Even if I can't say what the identity component should mean, maybe in a general sense, I can still say what derived invariant means. And this is the conjecture I put forward. And this is maybe not, at least this is reasonable for many reasons, some of which I certainly won't talk about, but it's also something similar in geometry, remarkably similar. So if x and y are derived equivalent projective varieties, then Roquet showed, this is unpublished work, but it's mentioned in Heubrecht's book on Fourier-Mukai transforms, that, well, maybe not the individual Picard groups and automorphism groups of x and y are the same, but the semi-direct product is a derived invariant. So this is very similar to sort of the situation upstairs, where this seems to be the case. And we see like examples where this happens. Okay, so now I basically want to finish with an example where you can study all of this and use the exponential to determine the complete derived Picard group. And this is about Fukaya categories and generalized algebras. So we'll be brief with the definitions. I think some of you might know them. The others, sorry, I tried to, hope you get some idea. So the definition goes back to Haydn, Katsakov, and Kontsevich, who started with a surface which comes with a set of decorations, and these are sort of distinguished points on the boundary or on the interior. And then an extra thing, which is a line field, and that's sort of like a vector field, but you just forgot about the direction of your flow lines. So there's an unoriented version of a vector field if you want. And then to this datum, you can associate an infinity category, which is a Fukaya category, which is called the partially wrapped Fukaya category. And one of the things is that if you put mild conditions on the surface, it doesn't work in all cases, but in a lot of them, most of them, then you can rewrite this Fukaya category as the perfect complexes of some algebra, which is a graded algebra. And this is so-called gentle algebra, which sort of was a class of algebra, well, not much longer than this kind of business of Fukaya categories in the ungraded case. And then they happen to be homologically smooth, whatever this means, not important. But you can also look at the Kojoule dual side, and then you get also graded gentle algebras. But in this case, they're finite dimensional, not necessarily smooth, whereas the other ones are smooth, but not necessarily finite dimensional. So you kind of have this duality there. And you can sort of go back. So from a surface, you can go to a gentle algebra, but you can also go back. So if you start with homologically smooth or finite dimensional graded gentle algebra, you can cook up a surface and a line field, and that is the inverse of that correspondence. And then you might ask, okay, how tightly linked is the surface to the algebra? and as a result by a bunch of people. So that says that if A is finite dimensional gentle algebra, or more generally a homologically smooth and finite dimensional great gentle algebra, then the surface in the line field depends on up to the theomorphism and so forth, only on the derived equivalence class of A. And the ungraded bit is due to Amiot, Clamardon, and Troll, and then independently by myself by very different methods. And then there's an update by Unishwan 1, which does this homologically smooth and finite dimension. And something which I won't get to say is that you can, with the stuff I'm doing here, you can do this very generally for all partially wrapped Fukaya categories, and you can therefore drop the homologically smooth end and replace the end by an or. So you can cover all the cases. So this is true more generally, but yeah, so will come out and hopefully soonish. Okay. So what's the theorem? So what's the derived Picard group? I think I'm almost done, so I will just finish after this slide if that's okay. So this extends earlier work by myself. So if you have a finite dimensional graded gentle algebra, and earlier it was just ungraded gentle algebra, so this brings its own complications, which has its surface, then either the characteristic of the ground field is 0, in which case we can use the exponential, or under some mild conditions on the surface, then we can also do it in positive characteristic. You can get a complete descriptions. And if you remember this derived Picard groups of derived discrete algebras, which are a subset of those, there was this mapping class group showing up. And what is the mapping class group? So roughly speaking, these are diffeomorphisms of your surface. But you have a bunch of structure, like these decorations, the line field, and then you can sort of also mimic the shift functor on the geometric level. So this is where the graded stuff comes from. And then you consider all of this up to isotopy in the system group that is called the graded mapping class group. So that's the geometric part that I was talking about. And then there's a more algebraic bit, and this is exactly this what I put forth as the identity component. In particular, because sort of the surface and the line field don't depend on the derived equivalence class. If I give you any other gradient algebra with this derived equivalent to this, it has the same part here. And you can see this really as, okay, this is the identity component, at least morally, and then you have this sort of quotient of the derived Picard group by the identity component, which is a sort of discrete group here. And you can sort of generalize this to in all sorts of ways. So you can do homologically smooth great gentle algebras. You can do all these Fukaya categories, which includes the cases where you can't model this by gentle algebras. So you can do similar stuff there, which I'm not going to mention. And then just like, I think it's interesting to maybe say that. So you can explicitly describe this group. And so this has like 3 components. So one is like this WK, which is the group of bit vectors, or you can also say continuous automorphisms of the power series ring is another description. They're like more known in number theory, I guess. And they come as the exponential of a sort of famous Lie algebra, namely the Derived algebra, or more precisely, a completed version of some parts of it. But so this kind of shows up very natural, and it would be very difficult to determine this part without the exponential, which is also one of the reasons why I need characteristic 0 for all cases. And then, okay, R and S mean certain number of boundary components on the surface. And there's one thing about this kind of invariance of this group out circle infinity. So this part, this cohomology bit from the surface that shows up here in this group always sits in this auto-automorphism part, whereas the part from the bit vectors always sits in this integrable part. It comes from the exponential. But then you have this third type of contributions, the additive group, and they can lie in either of them. And if you change the derived equivalence class, what typically happens is some of these copies go from, let's say, the auto-automorphism group into the part which comes from the exponential, and they jump between them. And so this is why they're individually, they're not derived from varying, but the semi-direct product altogether is. And that seems to be a general pattern there. And then, yeah, okay, some proof and some stuff. I think I finish here.
I forgot. Wow. Thank you. Do we have any questions in Buenos Aires?
It doesn't seem to be the case.
Okay. Okay. No, I'm still amazed how the mapping class group come to.
We can't hear you, Pat.
Sorry?
We can't hear you.
Yeah, it's good.
What is the graded mapping class group? I mean, until we learn what I was going to say is I'm still I'm crazy about the mapping class group appearing there in the. But what is the
Where sort of symmetries of the surfaces sort of show up. So yeah, the reason is sort of morally as though this derived category sort of, or the perfect complexes of A, you can sort of model all the objects in there. There's a classification of the indecomposable objects, and then there's a relationship between a way to map these indecomposable objects, isomorphism classes of those, to curves on the surface that is associated to the gentle algebra. So, and then you kind of view, you can actually take not only things in a derived Picard group, but any autoequivalence of your derived category of the gentle algebra, and just see what it does to these objects of the indecomposable objects. And that mirrors something, how sort of curves on the surface are sent to curves on the surface, which is also done by a mapping class. This maps sort of curves up to isotropy to other curves up to isotropy. And you just try to match this, and this doesn't prove you the existence, but this is sort of the idea why this should exist. So you get a map from an equivalence, and you just track what it does on objects, and you can interpret this, what it does on curves. And there's a sort of reasonably unique element in the mapping class group that does exactly this on curves, what you wanted to do on objects. If that kind of makes sense. Maybe this was a bit fast.
No, yes. Thank you. Yeah, I think okay. Any question? Okay. Well, please. Thank you again, Sebastian.
No, thank you. Yeah.
Wow.